So I'll give you all a couple minutes to try number 2 or 3 if you get there, and then I'll talk about the answer to 2 and 3. Okay, so did anyone get an answer to 2? Have a guess?
I got positive infinity.
Positive infinity. So A. Anybody else get an answer? Cool, yeah, so Evelyn's right. That is A. Good. Yeah, so if you're checking on the right side of -4, that would be like a -3.9. So if you plugged in -3.9, then you get positive 3.9 over a positive number, because I'd have -3.9 plus 4. So if I divide, and this answer on the bottom, I don't know why I'm choosing such a lavenderish color, but it's just hard to see. I like lavender, it's just hard to see. 3.9 divided by a positive like 0.1, remember, is a pretty large number. It's 390. So for us, like what's happening under the hood of this rational function is division by a small number, which makes the right side of -4 go to infinity. And of course, you can prove all these with a graphing calculator, but to know what's actually happening here, like you can prove it to yourself visually what's happening with a graphing calculator, but to know what's happening more at an algebraic level is going to be more beneficial to you when you start to look at more complicated limits. For number 3, you should have got A, and I'll let you all reason that one out. It's going to be pretty similar to how we did 1 and 2. Know that you can factor some of these. This one, however, is not factorable, so you just have to plug in a negative number that's on the right side of 4 and work through that. A lot of these, if you can tell, like I'm not doing a lot of calculations in this, but it's important you have a little scratch workout, so you can maybe do a little thing like that. For number 4, this one is different, so I'll show you all what's different about this one. This is asking for a limit at a value. So this type of limit requires the left side limit to equal the right side limit. And I know some of you all remember this, but probably a lot of us have forgotten. So as x approaches 2 from the right, that thing needs to be equal to the limit. So the y values on the left and the right have to equal each other. Has to equal the limit as x approaches 2 from the left. So is what's happening on the left side of this thing, of this function, equal to what's happening on the right side of this function at 2? So we kind of need to know what's happening there. This is a rational function. If you factor the denominator, factoring with rational functions tells us everything we need to know, usually. It'll tell us where to go with it. So I've got negative x plus 2, well, I'll just do negative x minus 2, and then I factor x minus 3, x minus 2, and at this point you should be like, oh yeah, I remember these rational functions. Someone besides Evelyn, do you all know what's happening at these factored locations? Dividing by 0? What do you mean? Oh, yeah. So the denominator would be 0 if we plugged in x there. I agree with you with that, but it's not an asymptote. Yeah. No, but no, you have the right logic to set it all up. What's the other thing that makes, I guess, if I said it, then it would, yeah, a hole. There would be a hole in the domain. So, at 2, there's a hole in the domain. But there's a hole, so like, if we remember, maybe I can sketch something that has a hole in it. This might not be the exact graph. Does a hole have a left side that approaches the right side? So here's another example of a hole. Do the two sides approach each other? Yeah, they do. So they don't spread apart like asymptotes do. So if we have a hole, then we actually have a limit because the left side of the hole and the right side of the hole, so this 2 x approaches 2 from the right and x approaches 2 from the left, they do equal each other at holes. So if, for example, we have the same graph and there's a vertical asymptote, so it asks for what's happening as the limit approaches 3, then we have a big problem. That would be A. That would be the limit doesn't exist. So instead, to figure out what's happening at this limit, we are just going to get rid of these. We're going to factor away, we're going to divide away the x minus 2 terms and be left with this negative 1 over x minus 3. So this will actually tell us what's happening to the y values at 2 if we just plug in 2. So there's nothing special happening at 2 if we've taken out the holes. So, or the factors that are contributing to the hole. So if we plugged in 2 to this function, then we're going to get negative 1 over negative 1, and we'll get d. So this last answer is D. So again, this is just a convoluted way to ask what is the graph approaching at 2. And it's not very clear at first because it's not factored and we haven't divided out the factors, but once we know that, well, it's just a hole and we can remove the hole, then it's just a simple like plug and chug. So this is like this is definitely more like on the advanced side of this class, but it's definitely worth mentioning to just show you that this function looks like that. I graphed it clearly at 3. We have a problem. There's no limit that exists at 3, but if we asked about the left side limit at 3, which we're not on the question, we would answer infinity. If we want to know what's happening on the right side of 3, we would say negative infinity. Y is going towards approaching negative infinity. And at 2, you'd see that we have a hole because of the factors that we showed earlier. So if we were to remove that hole again, your calculator and other forms would tell you what you would be finding. So negative 1 divided by x minus 3. And then we would just look at that to get 2, 1. So there's a lot of graph analysis with limits. I have been recording this a little bit, the back end of it, these last 2 questions. So if you want to go back and revisit this, you're welcome to. For you all though, are there any other questions?